Good evening. Today I will be speaking about memory management. First off, we will start by introducing what memory management is. Memory management is the process of controlling and coordinating computer memory, assigning portions called blocks to various running programs to optimize overall system performance. Normally, memory management resides in hardware, in the operating system, and in programs and applications. Hardware such as the RAM, random access memory chips, the memory caches, and flash-based SSDs, which is the solid-state drives, are also what's managed. In the OS, memory management involves the allocation and the constant relocation of specific memory blocks to individual programs as user demands the change. At the application level, memory management ensures that the availability of adequate memory for the objects and data structures of each running programs at all times. Application memory management combines two related tasks, known as allocation and recycling. Now that we know what memory management is, we shall move into our main operating systems that's being used as topics today, which is Android and Windows. We'll start with Android. Android employs several memory management methods, which are switching, memory sharing, garbage collection, restricting app memory. So we'll introduce the switching of apps. When users switch between apps, Android keeps the apps that are not foreground, that is not visible to users, or running a foreground service like music playback, in a least recently used cache. For example, when a user first launches an app, a process is created for it, but when the user leaves the app, that process does not quit. The system keeps the process cached. If the user later returns to the app, the system reuses the process, thereby making the app switching faster. Memory sharing. In order to fit everything in the needs of a RAM, Android tries to share RAM pages across processes. It can do so in the following ways. Each app process is forked from an existing process called Zygote. The Zygote process starts when the system boots and loads common framework codes and resources, such as activity themes. To start a new app process, the system forks the Zygote process, then loads and runs the app's code in the new process. This approach allows the RAM pages allocated for framework code and resources to be shared across all of its application processes. Other than that, in many places, Android shares the same dynamic RAM across processes using explicitly allocated shared memory regions, either with HMEM or Gralloc. For example, Windows services use shared memory between the app and screen compositor, and cursor buffers use shared memory between the content provider and client. Next, Android also employs the garbage collection memory management. This allows pieces of memory that is no longer being used by the program. They are then freed back to the heap without any intervention of a programmer. There is two goals to this, which is to find data objects in a program that cannot be accessed in the future, and reclaim resources used by those objects. and that is the garbage collection. Next, Android also employs the restricting app memory, and this is to maintain a functional multitasking environment. Android sets a hard limit on the heap size for each application. Therefore, this will prevent programs from allocating too much space in the RAM. Next, we have Windows. Windows employs swapping methods, clustering methods, demand paging, file mapping, memory pools. We will now compare Android versus Windows and how they will compare to each other. Fortunately, I was able to find a research that was done based on these two operating systems. I was able to find a research that tested both the Android and Windows put through a stress environment for them to be running programs constantly and heavier every time. And what I have found is that Android has limits on its heap size memory, so this will prevent overconsumption on memory. Furthermore, Android is able to kill background threads whenever required to free up resources. Basically, Android tries to maintain processes for as long as they can before termination for new processes to occupy the memory. Next, the tests on Windows found that the Windows Mobile operating system supports virtual memory and therefore able to support more processes than the Android. As processes begin to saturate, the load gets heavier, passing the capability of the RAM size, so therefore the virtual memory begins to trash. So in Windows, as the trashing begins, performances are greatly degraded. But however, the programs are still able to run, just at a different rate. So from this test, we were able to conclude that both operating systems demonstrate a slowing of the applications as the memory load increases. Windows, however, shows a smaller impact up to a point. Once, however, the main memory is saturated, the virtual memory system starts to trash, and performances is greatly slowed down. Both the programs will run, but they will run very slowly. The Android system does not allow the machine to be overcommitted and will terminate idle apps to free memory. Hence, in my opinion, both the OS manages differently. Android is developed for more of a short-lived interactive applications, whereas in Windows, they support a long program with high performance, heavy load environment.